Hello, in this tutorial we're going to be discussing recursion again. This time I'd like to focus on how to use arrays with recursion. Now, we could certainly create a simple method that repeatedly calls the function recursively to display a different element in the array. The trouble with that is that from a performance perspective it's very easy to do that with a for loop, and there's really no advantage of doing it with recursion. So what I'd like to do instead is pick a particularly good example showing how we can build an array based on what the user types in. But we don't know how many things they're going to type in beforehand. So imagine that we have a do while loop, and I want to construct this while the user's not done. I want to read in the number from the user and then insert into an array. But the trouble is, I don't know how many things the user is going to type in, so we can't allocate the array beforehand because we don't know the size until we've actually done the loop. One could say, well, you could just prompt the user, how many things are you going to type in, but what if they don't know, or what if this is coming across a network stream? So there's a great example of constructing an array based on what the user types in, and we don't know what they're going to type in, and we don't know how many things they're going to type in. So I want this same type of structure where I'm going to keep repeatedly asking the user for input until they say quit or that they're done, and then I want to construct the array based on that. And it's really quite impossible to do using iteration and a do while loop or even a for loop because we don't know a priori how many things they're going to type in. But recursion gives us an excellent way of pulling this off. So let me say that I want a new public static integer array. I'm going to call it build array. And I'm going to take in a count. Now count isn't how many elements we want the array to hold, rather it's how many elements we've already read in. And we're going to use this, and we're going to use recursion to actually construct an array exactly of the correct size based on what the user types in. I'm going to need a scanner here, bound to system in. Let's go ahead and fix the imports here. So we'll bring in Java util scanner. Okay, and then I'm going to prompt the user to enter the next number and tell them to type in -1 to quit. Okay, this is system out print because I want it to remain on the same line. And then I'm going to have a value. Sorry, let's just keep it even simpler than that. And read in the next integer from the user. And if the value is not equal to -1, then I want to return a new, if the value is equal to -1, this is my terminating case, to say the user, we've continually asked the user for them to type in values, and ultimately they end up typing in -1, and so I'm going to create a new integer array based on how many things I've typed in. So here's the use of count. So what I'll do is imagine the user types in 1 and 10 and 20 and then -1. The recursive stack is going to build up, and we're going to save the 1 and the 10 and the 20. Eventually when they type in -1, we're going to allocate this new integer array and return it, and then we're going to be able to populate the array once we have reached the maximum space in the stack. So I'll create a reference here, and it's going to be equal to build array of count plus 1. Now that's us moving closer, right? We're calling this function recursively again, and I'm going to set the array that is built to be what comes out of this recursive function call. And then I'm going to set the result of count to be equal to whatever the user typed in. And then I'll simply return result. Okay, so what have we got here? Simple recursive function. The complexity comes in the stack trace. So we'll examine this in a second. We read in a value from the user, and if they give us -1, we're going to allocate a new array based on how many things they've typed in. Otherwise, if they didn't give us -1, we're going to call this function recursively increasing the number of things we have recorded that they've typed in, and in this frame on the activation stack, value is going to be stored. So I'm not going to actually make use of what they typed in, and I'm not going to place that into the array until after the function recursion happens. Once we have recursively called and we come back here, we know that the array has been allocated, so I can fill in the proper space with what they typed in. Okay, so up here in main, let's create a reference and say I want to build this array, and I need to seed this by passing it 0, meaning I haven't actually created or haven't input any numbers yet, so we're going to start this off with the value of 0. Okay? And when that is finished, when the build array function is finished, I'm going to display the values out. So I'm going to iterate across my entire array and print out the value. And then go on to the next line here. So we're going to call build array in main. Build array is recursively going to repeatedly ask the user for values, and eventually when they say we're done and we want to quit, it's going to allocate the space large enough to hold all the values that they typed in, and then it's going to, as the activation stack comes back down, fill in the array until it comes back to main. Okay, so no loop here, it's just recursion, and let's run this. And what we'll get is it's asking us for values. And when we're finished, we'll type -1, and then it will have allocated an array large enough to hold the values that I typed. Now, notice that the build array isn't just simply displaying the values back to me. That would be easy enough to do. Rather, we're actually allocating memory to hold all of the values that the user typed in, and I didn't know a priori or beforehand how many values they were going to type. I just was able to use the power of recursion to pull that off. Now let's actually run it in debug mode so we can see the stack trace building up. Notice here we're in main. Let's switch over to output and type in, let's say our value 42. Okay. We go here and type in more values. You can see that no matter how many I type in, it's going to hold on to all of those and build the array large enough for us. Now that we have the ability to fill in an array with what the user types in, let's do an example on another great use of recursion, and that is the binary search on arrays. Now, if we have an array that's unsorted and all the values are just kind of jumbled in there, then we're going to have to do a linear search and examine from the beginning to the end all of the different values in the array to determine if what we're looking for is present in the array. If we have our values that are sorted, then we can use a binary search approach, and that is start in the middle and look to see, hey, is this thing I'm looking for right here in the middle? And if it's not, since everything is sorted, I can cut in half the work that I have to do. I can say, if the thing that I'm looking for is bigger than this thing in the middle, then just look at the last half. But if the thing that I'm looking for is less than this value in the middle, then look at the first half. And then repeatedly do that process again and again and again. We're going to do this recursively, and it's pretty easy to articulate in code, and it improves the performance of our search very much. It's going to give us the ability to search very, very fast. So let's imagine that we have built the array and we'll display the values back to the user. Let's say we've got a location, and I want to determine the location of a particular value. Let's say I'm going to search on the value 42. And then once that's done, we can say that 42 appears at position location. Now I haven't written search array yet, so let's write that. It'll be a public static int because it's returning the index or the location of the value that we're looking for. And it takes in this value to find. Now, the problem with this is that I'm going to need to call this recursively, but I don't have all the information that I need here in the parameter list for this function. So I'm going to actually call another function. I'm going to call it recursive search. I need to pass it the data, which I left that off here. So we have the integer array that I'm searching on and the thing to which I'm looking for. So I'm going to pass this recursive search function the array. I'm going to say I want you to look between the 0th element and the last element, and I want you to find this thing. So notice I'm adding on 2 parameters, and these are the indices that I should focus on within the array, and that's the power of the recursion that's going to come here. So I'm going to have a public static int recursive search that takes in an integer array data, an integer minimum, and an integer maximum. These are the array bounds that I'm focusing on, and an integer to find, and this is the thing I'm looking for. Okay, now we can actually get down to the recursion here. Let me go up here and actually pass in my data. I left that out when I added my second parameter here to the search data definition. Okay, now we can actually focus on the recursion. Now our terminating case is going to be that when max and min have crossed, right? That means that I've looked, I'm using the max and the min to determine the space that I'm looking for in the array, and if these have crossed over each other, then I know that I've looked at everywhere the number could possibly be, and I haven't found it yet, so I'm going to return -1, which means that we didn't find the number that we're looking for. Otherwise, I'm going to calculate the middle position, which is the max plus the min over 2, or the average between these two, and that's going to give me the index in the middle within the range min and max over the entire array. Because I don't always want to look at the entire array, I want to keep cutting smaller and smaller and smaller. So middle is going to be the index at the middle position of the range min to max. And if the data that I'm looking at this middle position is equal to this thing that I'm searching on, then I know that I've found my match and it's at position middle. Otherwise, if I haven't found a match and I still have somewhere to look, then I'm going to look at the middle position, and if it's bigger than this thing that I'm trying to find, then I know that the place that I'm looking for, or that I should repeat and focus my search, is on that left half of this middle section. So I'm going to return the recursive search on the entire array. I'm still going to keep my minimum, but now my maximum is going to become middle -1, and I'm still going to pass it this thing that I'm looking for, this to find here. Okay, so if I haven't run out of space, and I haven't found a match, and the thing that I'm looking for is not less than the thing that I'm looking at right now here in the middle, otherwise I'm going to return recursive search. So here's an example of a function, a recursive function that has kind of 2 paths that it can go down. It can go down the left path, or now we're going to look at going down the right path. So my new minimum is going to be the middle +1, meaning look to the left-hand side, and maximum is going to remain the same. And here's the entire function. So if I don't have any more space to look at, return -1, meaning the value can't be in the array. Otherwise, if I find the match, then great, return this index here. Otherwise, if the thing that I'm currently looking at is bigger than this thing I'm trying to find, then look to the left, and these indices indicate going to the left. Otherwise, I need to look on to the right section of this array data structure. So back up here, in main, I'm going to look for the value 42 and call this search array function, which is going to in turn call this recursive search function, seeding in the range of where I want to look. Here 0 and data.length, that gives me the entire array. And I'm going to recursively and repeatedly look at smaller and smaller subsections of the array until I find the spot where 42 occurs. So let's run this. First thing we're going to have to do is type in the different values. Now, key here is to make sure that they're sorted. If they're not sorted, then we can't perform a binary search on this array. So I'm going to type in some different values. And if I type in -1, I'm done keying in all these values, and it's going to give me back my values and then determine where the value 42 appears. Recursively on the binary search, we're going to start here in the middle, and 42 is less than 100, so I'm going to look at this subhalf of the array. Then I'm doing a comparison on 31, and the value 42 is bigger than that, so it's going to look here, and it'll look for the middle. Rounding down, it'll find 42, and it correctly determines that this appears at position 3, which is 0, 1, 2, 3. And that works just like we would expect. If I run this again and type in new values, 9, 41, 90, 200, and 999, and I'm done. And notice 42 doesn't appear in this array, and it's going to give me back position -1, which indicates that the value 42 doesn't appear in the array at all. If you'd like, in recursive search, you can put some output here. At the beginning, perhaps, you could say system.println, system.out.println, searching between min and max, and you'll see the search going on then. I need a plus there. Okay, so we run this and type in our numbers. 9, 31, 42, 90, 105, 400, and 987. Let's do a few more just for good measure here. And now that we're done, you can see the activation stack is displaying the recursion here. I'm looking between 0 and 9, looking at the entire array, then between 0 and 3, right? Then between 2 and 3, and you can see that it's whittling down slowly but surely the range that it's looking at as it goes until it finds the correct value. Okay, so the takeaway from this tutorial is that we can use recursion on arrays. A really great example of the benefit of recursion is this situation here where we built the array. We didn't know beforehand how many values the user was going to type in, so we deferred the creation of the array and filling in the values until the activation stack had built all the way up. As soon as we got to our terminating case where the user didn't want to type in any more information, we allocated the space in the array here using our new command, and then as the activation stack comes down, we filled in the array with values. It's a great way of showing how to use arrays and recursion in a very useful manner. And then we developed this array binary search where we looked at increasingly smaller spaces within the array and cut the work in half every time to get a very, very efficient search. Now, if we had a small array, the binary search benefit doesn't really show, but if we had millions of values, then doing this binary search is going to be much more efficient and fast than if we did a simple linear search across the entire array. Since we're cutting the work in half, we're going to do logarithmic work. So we can double the size of the array and only do one more step of work, and that's really, really cost efficient. And that'll do it for this tutorial on recursion and arrays.